All right. Thank you, Andre. Thank you, Zoe. Thank you, everyone. So thanks to those of you who are here in person, and thanks to everyone who has joined us online via Zoom. My name is Jenny Sabin, and I'm an Associate Professor of Architecture here at AAP. And I'm also co-chairing the university-wide Design plus Technology Faculty Task Force together with my colleague, Wendy Ju. So this is the second lecture in our inaugural lecture series, which is titled with the question, what is design plus tech? This inaugural university-wide lecture series explores design research, technological innovation, scholarship, and collaboration across disciplinary boundaries in science, engineering, and design. The series is represented by a network of colleagues and faculty from across AAP, the College of Human Ecology, Engineering, CIS, ANS, as well as faculty at Cornell Tech. In an era where we are witnessing one of the biggest paradigm shifts in the conceptualization and creation of our environments, objects, and interfaces, the series will present research and projects on topics at the intersection of design and emerging technologies to understand and discuss their impact upon industry, practice, knowledge production, and pedagogy in a changing world. Highlighted on the screen right now is the breadth of the series. We kicked off on January 26th with colleague Itai Cohen. If you did not have a chance to join us for Itai's lecture, I encourage you to watch the recording, which is also available on this page. And it is my sincere pleasure to introduce my colleague Timur Dogan, who is giving us our second lecture this evening. A little bit about Timur. Timur Dogan is an assistant professor at Cornell AAP, and he holds a PhD from MIT, a master's in design studies from Harvard GSD, and a diploma of engineering and architecture with distinction from the Technical University of Darmstadt. Dogan's mission with Cornell and the Environmental Systems Lab is to enhance the knowledge of sustainable building technologies through the innovative educational programming and strategic research at the intersection of design, computer science, and building performance simulation, as well as urban geospatial analysis. The outcomes of the Environmental Systems Lab's research are sustainable design analysis methods, workflows, teaching concepts, computer-based design tools, and facade components. So I encourage all of you to visit the lab's website and to take a look at their many published papers, as well as awards and accolades achieved over the recent years. So please join me in welcoming Timur and his lecture, which is titled Augmenting Design with Environmental Performance Analysis. Thank you.
Thank you very much, Jenny, for this wonderful introduction, and thank you very much for having me as part of this series. And so I wanted to talk to you today about augmenting design with environmental performance analysis. And I brought a few slides to introduce myself, and obviously then two projects to talk about. So my role here in AAP is also to teach, and I teach basically fundamental courses on building science and then more advanced research seminars kind of in the field of building performance simulation and analysis, performance-driven design analysis, and these kinds of things. Occasionally also design studios, usually with a collaborator. And I also am directing a lab, like Jenny said, which I think was housed in AAP, but draws from many of the diverse students here on campus, from across the campus. We had planners, computer scientists, we had environmental engineers, systems engineering students, and many more. And I think this is a great place to kind of exchange ideas. And I'm really happy. And all of the things that I'm showing you today, obviously, is big thanks to the students who are kind of helping me with this mission in the lab. So why should we kind of augment design with environmental performance simulation? What is the motivation behind my teaching and my research? So if you think about it, well, we have to, our profession as architects, we're charged with kind of decarbonizing the built environment completely by 2040 to reach this 1.5 degrees C climate change target. And at the same time, we're seeing a trend towards urbanization and population growth that essentially means we'll be doubling our built floor area by 2060. So in a sense, and that is really kind of worrisome if you look at what the current kind of carbon contribution of buildings really is. And you see it's 1/3 is just building operation, meaning heating, cooling, lighting, and these kinds of things. 10% of that is the construction industry. And if you think about the built environment as a bigger concept where all of a sudden it also influences how we move through cities and these kinds of things, then we include transportation. So we talk about almost half of the carbon emissions globally that we can somehow link to the way we designed our built environment. And with that, maybe a little bit about the philosophy from where I'm coming from. The idea really is, for me, if we kind of design cities, if we design buildings, that these designs should always be a smart response to the environment and the context to make pleasant spaces for people to live in. And the thinking behind my research really is that we use technology to augment the design process so that we can empower designers to reach better solutions to this performance-driven design idea. And what are the things that we are interested in looking at? So these multi-objective performance criteria, at the center, obviously, it's the human experience, like how comfortable are we in buildings and how well are we doing in buildings? And then, all of the other things that kind of relate to kind of environmental science, from energy, carbon emissions, how do we move in cities, mobility related questions, daylight availability in buildings, and lastly, also the life cycle aspect and the materiality aspect of how we construct our built environment. And these topics are so broad in the sense that they range across many, many scales, and we kind of have to work at these different scales, ranging literally from the building component scale to the city and neighborhood scale to kind of get a sense or how meaningful and impactful some of those things is. Because sustainability, in a sense, doesn't stop at the building. You have to kind of consider the bigger context in many of the cases. So why should we consider integrative design? And I'm always kind of citing this really, really old theory from systems engineering, or especially naval engineering in this case, where smart people kind of figured out that really in the design process, especially early on, there's a lack of information. And as designers of the built environment, we face that exact same challenge, that in early design, we really have a lack of information about what the design will actually be doing once it's completed. And if we had more information, then we would be able to tap into a significant optimization potential, and we could potentially also make decisions much more quickly and therefore save a lot of time in the design process. So the conventional way of doing design today, in many cases, often is we have an idea, we design, we finalize that idea to a degree, and then at the end, there's some kind of analysis that comes actually from an engineer, probably, who was brought on as a consultant at a different time, or at a later time. And then it's often really too late to make really radical changes to the design. And I think the goal here really is to push the evaluation component really into the early design phases, and also to make that collaboration between the engineering disciplines and the design disciplines easier at an early stage of the design, when some things are maybe vague and not defined and not that easy to analyze. And for that, to make that possible, we really need three things, I believe, which is new tools that have easy to use interfaces with to lower the barrier of actually this wider application of the analysis. We need new algorithms to speed up simulations and to automate tedious tasks that disrupt the design workflows and creative thinking. And we need new metrics because we need to, as designers, really ask ourselves, like, what are the things that we care about? What are our core values that we want to somehow account for in these kind of analyses? So just one example, and this is showing a software tool that I co-developed with 4 collaborators from Harvard as part of a company called Solema. That is, software that is taught at over 300 universities globally, and many of the leading design firms are our customers, and we are very, very thankful for that. And that exchange is really has brought the software tool a long way. And the idea behind the software really is that you embed the analysis directly in the software where people design. So this is showing you a screenshot of Rhinoceros 3D, which is a popular 3D modeling interface. And the Climate Studio analysis tabs are basically directly integrated. The results are mapped onto the geometry that the designers actually created. And then you can start a cycle. You can start this design cycle, performance analysis cycle, where you kind of interpret the results and then you iterate. So kind of you design, you validate your ideas, you adapt them if needed, right? And you can leverage this tool also kind of in a more parametric world where you can search design spaces more rigorously. In this case, showing kind of an example of the Sana Zollverein building in a parameterized way with the goal to balance out daylighting, prevent glare, prevent kind of dark spots in the deep floor plates that you're seeing here. And by just manipulating position of windows and manipulating the size of windows, you can kind of do this really quickly. So just to give you an example before I jump into the project. So the project that I wanted to talk to you about today is the Toronto Waterfront project, which was initiated by Sidewalk Labs, and I was kind of pulled in as a consultant with a team at KPF working on this project, especially kind of looking into the performance analysis and parametric design approaches that Sidewalk Labs was interested in trying out. Okay, so the project was really, obviously, you may have heard some of the discussions in the news. It was controversially discussed, and for many good reasons, and rightfully so, I think. But at the core, the project really, or our task was to come up with a design strategy for a walkable, comfortable, well-lit neighborhood that is in the end also CO2 neutral. And so what is interesting about this project is really kind of this design approach that was implemented there, where urban designs were procedurally generated with very loosely defined kind of geometric design outcomes as goals, and so to do a broad search through many different urban design iterations, and then understand certain relationships and understand performance trade-offs once you do some form of an analysis on these different designs. So there was a design generated, then there was an automated translation between the design representation and then also the simulation models that the inputs into the simulations, and then there was an automated performance analysis. I don't see it. Yeah, so. Yeah, I don't know what this window is that's popped up. Okay. All right. Some technical glitches. All right. So when you think about urban design and parametric urban design, we are all of a sudden operating at a scale where the performance analysis, the tools that we have in our arsenal are really not feasible to use anymore, because running a single building simulation takes about half an hour. Now thinking about doing this for many thousands of buildings really becomes unfeasible. So One example of a new kind of way of thinking about energy modeling at the urban scale is actually work that I did for my PhD, where clustering was used to basically reduce the complexity of kind of an urban model, while at the same time kind of keeping the geometric fidelity and the localities of where energy is used at what time, and being able to map that. And this software was able to do this about 250 times faster than traditional, energy modeling workflows, and is now implemented in a software tool called UMI, which you can download for free from MIT's Sustainable Design Lab. And the way this really worked in the background is that the software kind of automatically differentiated perimeter regions and core areas, then does a solar analysis on the envelope to figure out where are high solar gains, where are low solar gains, where would you have an abundance of daylight, where would you have trouble actually getting some daylight in. And then the facades of all of those buildings are clustered. What is defined are typical rooms. So we kind of go from a very, very abstract urban scale to a room scale, and we can do our analysis at a very, very high detail level. And then these rooms, these typical rooms, are then mapped onto kind of the building and also the entire city. And with that, you can achieve kind of these performance gains. In a similar way, you can also do fast urban daylight analysis, and I want to kind of just show here this example where where daylight potential was analyzed on different massing model ideas that then were scaled in terms of their density to almost absurd levels, just to kind of understand how does the performance of or the availability of daylight change with an increase in density. And when you map it on a graph like this one, where the daylight availability is on the y-axis, and the higher the better, and the density is on the x-axis, measured in floor area ratio, you see kind of something very interesting, that most of these design configurations actually drop below a performance threshold of 45% at around an FAR of 12. But one just keeps on going. You can double the floor area without really sacrificing access to daylight. And I think this is something, even though this is a very simple one-dimensional analysis, shows the value of of what the designer's contribution could be if they can quantify these things, right? So this is something that is a certain value add in a design experiment, as we had seen kind of for the Sidewalk Labs project. Another topic when we design at an urban scale, obviously, is we're not just interested in making our buildings work on the inside, but we want to also kind of create comfortable outdoor environments. And as you see in this picture is from Foster and Partners, that they did this for their master plan in Abu Dhabi, where you can kind of take this as evidence that the built environment really significantly influences how usable the outdoor spaces become. So just by creating narrower streets and using overshadowing in the same climate zone, you can achieve a much more pleasant outdoor environment. And so again, the designers are kind of tasked here to kind of include this in their design processes. So when we talk about outdoor thermal comfort, there are many ways this can be abstracted or modeled. The most common way is using a metric called Universal Thermal Climate Index, which was developed by the German Weather Service in 2012. And this is a model that I think is very, very sensitive and to kind of the human experience, and it requires fairly simplistic inputs, if you will. It's just a meteorological input. If you have a weather station, you can just measure these things like air temperature, radiation, humidity, and wind, and then that that goes into a physiological model. There's also a clothing model applied that automatically kind of changes the clothing of people from kind of shorts and t-shirts to thick winter clothing, depending on the meteorological input. And then you can get a modified temperature, if you will, which can be then related to these kind of heat stress and cold stress conditions. Now, in an existing city, measuring this is straightforward, but in a design, this is actually much harder to quantify, because many of these inputs are highly influenced by the built environment, and therefore need to be simulated with fairly complex physical simulations. And so my lab is working on a software called Eddy, which makes this easier, or which tries to give this kind of modeling capability into designers' hands in a sense. And again, a software that is has been quite popular, has downloaded many times, and it's been used in practice in academia, and there are more and more research papers that kind of leverage this software tool to kind of do certain analyses. And again, how is this? What in particular is interesting about the software? So we are leveraging open source engines such as OpenFOAM and Energy Plus to do the core physical simulations. But we do a lot of work on interface, and we do also a lot of work on automating some of the things that, such as best practice guidelines for CFD, so that a non-expert user can use this with confidence and without having to worry that the simulations become unusable if certain things are not really kind of taken into account from a setup perspective. And in addition to that, we also work on scalability of these simulations, such as using smart setups for CFD domains that allow us to kind of save time on meshing and save time on actual simulations, because we are doing these kind of models not just for one wind direction, obviously, but we have to simulate many different wind directions for one given geometry. And similarly for MRT, we kind of can do these kind of surface temperature simulations very well in small scales, but if you do this for an entire city, these models become complex, and you have to somehow reduce the complexity without sacrificing the spatial fidelity of these algorithms. And I don't want to go into much detail here, but so many of these things will kind of go into these software tool developments, and that therefore then make them accessible. We also use the campus as a living lab and do lots of measurements to kind of validate some of our shortcuts that we implement into these software tools. Now back to the Toronto project. So how can you use a software like Eddy in a meaningful way? So if you look at these two charts, at the top is basically the Toronto weather processed through this UTCI metric, and you see on the y-axis the number of hours in a day, and then on the x-axis basically every day is mapped or arrayed up. And then you can see the comfort rating, green meaning comfortable and blue meaning cold stress, and as it goes into the redder color tones, we're talking about heat stress. So in a very simple thought experiment, what if you could reduce the wind speed in the outdoor spaces, in the public spaces, and provide access to the sun in the winter time? And similarly, you would do something in the summer. You would provide shade potentially in the summer, and you would allow for exposure to a certain breeze to prevent overheating in the streets. And if you look at this analysis, you can basically increase the comfort hours by 26% by just slowing down the wind and providing access to the sun in the streets. And that doesn't sound that remarkable, but if you kind of say it in other words, during the day, the comfort when people use outdoor spaces most, you can extend basically the time period in which you can spend time outdoors. You can sit in a cafe or pleasantly walk or bike through the street. You can extend that by almost 4 months. And I think that is, again, you know, a remarkable, quite remarkable value contribution if you can showcase that your design or the built environment is actually creating that kind of an improvement to the current conditions in the city. Now, with that, you know, when we do these kind of outdoor comfort modeling, we model the perception of people in these spaces, but it's also interesting to kind of understand how people use these spaces and how they move through these spaces. So we also in the lab develop a software together with my colleague at civil engineering, Samija Samaranayake. We develop a software that tries to connect urban design, mobility, and sustainability. Again, you can download this free and use it. The way this really works is we use a data-driven choice model. So we take data from the Federal Highway Administration, the National Household Travel Survey data, especially the add-on data that has high fidelity kind of movement data of people. We take all existing census data and job data that we can get for cities and combine that with custom analyses of our built environment, including how much vegetation is there, are the streets thermally comfortable, and are there certain kind of street design parameters that we believe are important for motivating people to use more active modes of mobility. And then we train a machine learning model that predicts people's behavior, and that behavior is then kind of translated into trips that we can map in high detail for different modes, like you see in this kind of map in the middle. And we can use it to figure out how many people really kind of visit certain points of interest in the city, for example. And with this output, we can analyze travel behavior in cities quite in quite great detail, and we can then from there also calculate, you know, broader impacts, such as what is the impact on sustainability if I change certain things in the built environment. What is the impact on public health, for example, as well, right? And, you know, again, it's always important to kind of go back and see, you know, how good is our modeling in terms of reality. So what we are doing here, what you're seeing here is a map of Los Angeles, basically comparing our synthetically generated mobility data on the left-hand side, and on the right-hand side, we compare this to SafeGraph data, or the so-called neighborhood stops metric, which is aggregated cell phone data. And now this is actually, so you can see that Urbano can pick up the most prominent mobility patterns and recreate them. Now, why is this remarkable? Because first of all, SafeGraph data is really expensive, especially cell phone data especially is really expensive and usually out of reach for a design firm. And on top of that, and this is the most important thing actually, you cannot really use cell phone data to test something that doesn't exist, right? So this is something that Urbano allows now designers to test certain scenarios and changes to the built environment. And so when COVID started, we asked ourselves, how can we use our research in a meaningful way and help the city understand certain things? So we started building a mobility model together with folks at the New York City DOT, and also including people from KPF and colleagues from Cornell Medicine, to create a mobility model and then kind of relate that to COVID case rates. And the question that we really asked is, how do urban design, urban density, mobility, and access to service influence pandemic resilience? And we published a study recently, and we can see where we concluded that really long commute times and household crowding were the most prominent kind of indicators, and were strongly linked to high COVID case rates. So, you know, planning paradigms of, you know, the walkable city, high density cities are actually kind of, we can kind of support that and say that these are kind of planning paradigms that would also have helped in a pandemic like COVID. And then you all know the fate of the Sidewalk Labs project, but I wanted to kind of end on a nice footnote where I think some of the lessons learned from this project were really, really interesting kind of findings. And one of my favorite ones is really this this is from this community engagement workshop that KPF did in Toronto, where they invited Torontans to kind of participate in design and play through playful manner, kind of iterate through different design versions, modify the design, look at the performance indicators, and kind of learn how certain things are related and what are the trade-offs. And I think one of the lessons here was that, you know, this design space exploration can be a really, really useful tool to inform discussions with non-designers and non-experts, right? So with the people who we are actually building for. And, you know, these stakeholders or you know, our clients, they often also change their opinions and they change their priorities the minute they start to understand the relationships and the trade-offs. So it's a really, really engaging way to kind of communicate some of our work to the people who we are actually trying to help with our work. The second project that I wanted to kind of talk about is the Ithaca Green New Deal. Because when we talk about existing cities, we are facing a whole new set of challenges that are very, very different from kind of designing just on a blank slate. So the city of Ithaca decided to decarbonize. It's one of the first cities that in the US that that has voted for this and that has started to actually implement some of these measures. So again, you know, we see a similar kind of picture. The built environment is the one of the biggest contributors to CO2 emissions. And the city has pledged to kind of do this transformation through a couple of measures, working on transportation, you know, changing, electrifying cars, providing the charging infrastructure, promoting active mobility, changing our energy supply from gas and other fossil fuels to geothermal, solar, and then some kind of a storage component as well. And our buildings where we need to look into upgrading envelopes, densifying and adapting resisting buildings to induce or to kind of promote active mobility, and then obviously recycling of those materials that come from buildings that cannot be saved and need to be replaced by new structures. So this is a project that I'm doing with my colleague Felix Heisel, where we're trying to help the city inform this transformation process. Similarly to the design, the early design issue where there's a lack of information, there's also a lack of information really on how and where and when energy is consumed in our built environment. And to kind of answer some of these questions and to inform the transformation process and these measures that I just talked about, we want to use energy modeling tools to inform the city of the current status quo, and then we want to use these software tools to test scenarios and to kind of help the city find basically the biggest bang for the buck, right? When they do these implementations. So first challenge is we don't really have a lot of information on how the buildings are constructed in Ithaca. So the team worked really hard on kind of creating a typical creating typical constructions and informing a catalog of these construction archetypes. And we are in the process of kind of capturing some information on facade materiality on buildings and also the window sizes using simple image segmentation techniques, capturing this data from the city. And on top of that, we have issues with the geometry of the built environment. So all kind of existing workflows that are out there that can produce geometries from LiDAR data, produce geometry that is not compatible with our analysis software tools. So we need to kind of implement some custom algorithms to fit planes to point clouds and then create clean volumes that are then simulatable with the tools that I had mentioned earlier. And so if you put this all together, you kind of are able to actually create a building energy model of every building in the city. And then with the simulation tools, you can then try to model some of these decarbonization scenarios and test them and really kind of understand what the implications and the benefits and possible trade-offs are of this workflow. The nice thing is that this workflow that we are developing here is scalable and transferable. So if the next city wants to decarbonize, this workflow will be ready to use and hopefully helpful to them as well. And so some of the kind of outcomes that you would expect from a process like that is you can kind of map energy consumption at the city level, and you can understand, like, demand for heating and demand for cooling. Are there synergies? Can we do load sharing, for example? You can map energy consumption for every building, and you can figure out which buildings to target for retrofitting first. And then you can try all kinds of different retrofitting ideas on these buildings and then select together with the owners. And again, using kind of this broad search first and then decide later approach to kind of decide what would be the best scenario moving forward. And all of that, then obviously we have to somehow package for non-experts, and we're kind of working on this web interface that would make this really easy, and we hope that we can inform Ithaca's kind of sustainability policies with that. So I want to end on this slide, just kind of giving you an overview of all the different tools that Solema and my lab have developed in the past and that are out there. All of the tools that I showed you today are free for academic use, at least, right? And you can download them and put them into action if you want to. And with that, I want to end and thank you all for joining it, and for those who stayed in person.
Thank you, Timur. Really excellent talk. So we now have some time for questions and discussions. So maybe we can start with those in the room, and then we'll go to our Zoom participants. Quite a large audience on. Got a microphone.
So does it work? Oh, so I was just wondering where like the energy analysis fits into a typical architecture office, if the design team is sort of supposed to be taking charge of that, or if there's a specific occupation that's adjacent to the architecture field that's covering that analysis.
Thanks for the question. I think it's a really, really good question, because it used to be that there was a very, very kind of strict separation into these kind of silos where, there's an engineer and then there's a designer. And I think this is also maybe part of the motivation why there is this series of talks, because we want to kind of bring these two professions together. And I think there will be room for everyone in this kind of thing. So the software tools that I showed are meant to kind of push the analysis into early design. That often probably means that the designer herself or himself has to do this analysis, and it has to be easy enough for these kind of non-specialized people to do this analysis in a meaningful way. But at the same time, my hope is that these software tools become some form of a kind of common ground where you can hand this off to a specialist later on, who then does kind of play with the harder settings, let's say, of these kind of analyses, and that this becomes a way to kind of communicate and translate some of the complex technical implications that we are facing in buildings and cities.
So at this point, we can open it up to our Zoom participants. There are questions?
So a lot of the like softwares that you shared today, I didn't know about before. And I was wondering what would be some like key names to remember, or maybe just like the main set that I guess I should learn more about.
Oh, that's a really difficult question. Just remember my email address and I'll send that to you, or just remember the lab website and check out the tools that we're doing there. I think, it's really difficult to answer this question because it really depends on what your interests are and what you want. And I think they're all equally important depending on, what your interest is. And so.
Uli, you see your hand up? Go ahead.
Yeah, Timur, that was a terrific talk. I really enjoyed it as a person that has absolutely no knowledge in this area. It was incredibly interesting. It sounded like, listening to your presentation, that there are now, through your work and that of others, incredibly powerful tools available for, in particular, city redesigns, in order to basically address this sustainability issue. What is, from your perspective, the biggest hurdle to get that actually in use? Because obviously, if every city would go about and use your things, then that would be a huge step towards a more sustainable planet. So what do you see as being the most critical hurdles that have to be overcome to make that a reality?
Yeah, thanks a lot, Uli, for the comments and the question, obviously. It's a hard question also, in a sense that my thinking is that the tools that I showed you are still way too difficult to use. And we've come a very long way with making these software tools available and making them accessible. And somewhat easy to use, but I think there's still work to do. And especially at the city level, there comes the data question, right? So every city has different data formats in which they kind of store the information. Sometimes it's an Excel spreadsheet, sometimes a Word document with permits in it. And processing this data somehow into a usable format is a challenge. And then, I think if you kind of figure those two things out, I think you're in good shape. And then it maybe requires a little bit of kind of speaking to people, engaging with these people to understand what their difficulties are and what their challenges are, and what also are the questions that are trying to answer.
Thanks, Timur.
Other questions for those of you on Zoom? Great. So thanks again, Timur, for a really excellent talk. I have a question that I guess relates to what you were just discussing around data, how it's collected, how you're able to work with it in terms of access. And it reminds me of some of the current work of Benjamin Bratton, who is a theorist and architect, teaches in Southern California. And he writes about what he calls a sensing layer. And in the context of AI and the use of machine learning algorithms and big data, and that, to be sensed is to count, and to not be sensed is to not count. And he uses the example of, people who have access to testing for COVID. And so through your work, which is, very dependent on these data flows, are are there people or certain parameters or conditions that are climactic that are not currently being sensed and therefore not being counted, that therefore potentially influencing the analysis and the simulations? I'm just curious.
Yeah, it's very, very, very good question. And I think it's happening. And I think at many levels, because first of all, the things I showed you, they were very specific kind of analysis metrics. And you could argue that, in between these kind of 5-6 metrics that I kind of mentioned earlier in the beginning, there might be other things that are equally important, right? So those are kind of still in the hands of the designer's intuition to factor in. It's not that these are the only things to consider, right? So there's this component. And then, we have the traditional kind of bias in our analysis tools that if you take, for example, outdoor thermal comfort metrics in buildings, those metrics have been developed in Denmark, and then there have been human subjects that were kind of participating in these studies. And of course, they were all Northern Europeans, right? So obviously this metric is heavily biased in that direction. And every time I go into a conference in India, for example, people say, well, this comfort metric is good and fine, but I think it doesn't really apply to me. And they probably have a point there, right? So there's obviously this bias. And I think what our profession really needs to do, I think, is collect more data from more voices. And this is maybe the blessing of Zoom and the blessing of kind of social media, is that this is actually very easy to do at this point. And we could potentially kind of collect more information from other continents into this research. And what else? I mean, I think some of the mobility models that I showed, some of our earlier iterations actually of these models depended on exact locations of certain businesses. And just looking at that, so we sourced our information from OpenStreetMaps, and OpenStreetMaps is open and therefore very easy to access. But it only carried 12% of the businesses, for example, that Google has. And your analysis outcomes are completely different if you use one input set to another. And there's certainly a bias there. And there is also a certain bias, obviously, in the travel household survey data, even though there's a lot of attention is being paid that these things are not biased. But the sampling density is not high enough to really kind of exclude these things.
Thank you. Really comprehensive answer. Any other questions from our Zoomers or those who are here in person? Uli.
Yeah, if I'm allowed to ask another question, I would love to. Timur, I was just wondering, this may be out of the box, but kind of retro. Can you go back and use the design principles that you have evolved and go back to, let's say, to biologists, because kind of biology is the mother of all designs, and kind of use that to analyze biological designs to basically better understand those, and then use that kind of to improve kind of the artificial human designs? Is that something that makes sense?
Yeah, I think it does. I think it's not easy with what I showed you, but there are kind of possibilities to kind of do that. And there's, I think, whole areas of kind of people that are interested in this so-called biophilic design that I think try to make use of these things. I think that would be very interesting, and I think that it's a chance of kind of this series of talks to kind of get these conversations going.
Awesome, thanks.
Thanks, Uli. segment of what design plus tech can be. And my hope really for design plus tech is that, especially in the building context, we use technology to design better, to improve our design process, and therefore arrive at a solution that maybe requires a little bit less technology. And what I mean by that is that we tend to, when we just apply technology as an afterthought, we end up with very, very complex systems that are usually flawed. And so what I mean by that, technology in the design process, arriving at a solution that is simpler and better, right?
Thank you so much, Timur, for this fantastic talk. And thank you for those that joined us on Zoom and here in person. Next month, we will have our third lecture in the series of 4. And the lecture will be presented by Uli Weissner, who posed a couple of questions this evening. And that will take place on March 30th at 5 p.m. So stay tuned and please join us next time. Thanks, everyone. Have a really great evening. And thanks again, Timur.
Thanks.